We have Marco Picillo from University Polytechnical University of Torino, PhD student on aeroacoustics, and he's going to talk about his work on some multi-fidelity predictions, acoustic predictions. Okay, Marco, go ahead.
Okay, thank you.
Okay, I can bring.
Can you see the screen?
Yeah, I share the screen online. Yes.
So it's working. Okay, so thank you. I'm Marco. I'm from Turin. I'm doing my research is based mainly on multi-fidelity approaches for rotor noise prediction, and with my supervisor Francesco Vallone from Politecnico di Torino and my co-supervisor Mattia Barbarino from the Italian Aerospace Research Center. So I will start with a brief introduction, a description of the numerical approach we used in our calculations, the validation of low fidelity framework, and then we will see some validation with respect to transient angular velocity condition, tilting, and a single frequency harmonic gust for a single propeller. So nowadays, there's a lot of interest in urban air mobility, which its main goal is to improve the mobility in cities with many applications ranging from air taxi to delivery by means of electric vertical takeoff and landing vehicles, which are vehicles capable of takeoff and land in small areas, which are usually composed of multiple propellers. And however, in order to see a viable market, this relatively new concept needs to face some and overcome some important challenges related to safety and public acceptance. In particular, there are many reports that suggest that noise highly influences the public acceptance. Moreover, because these vehicles operate in a complex urban scenario characterized by non-uniform inflow conditions such as gas and turbulence, and in maneuvering flight that cause transient effects during the flight, which finally change the noise and its directivity in time and space. For this reason, it's important to predict noise under these maneuvering conditions and unsteady flight conditions in order to assess their impact on communities. There are many numerical approaches adopted for this, ranging from low fidelity to high fidelity. High fidelity methodologies are based on high fidelity CFD simulations with, for example, large eddy simulation, direct numerical calculations, Urans, runs, lattice Boltzmann approaches, while the low fidelity approaches are based on simplified aerodynamic solvers in simplified version of aeroacoustic solvers. Clearly, increasing the accuracy will increase also the computational cost. For this reason, it is infeasible to study complex maneuvers with complex numerical tools. I will describe just briefly the lattice Boltzmann very large eddy simulations. With this approach, the physics is described at the mesoscopic scale. The flow is modeled as a collection of particles, and the dynamic of this population is governed by the Boltzmann equation. On the left-hand side, we have the probability to find a particle in a volume dx centered around the position x and in the time interval t plus dt and in the velocity interval v plus dv. On the right-hand side, we have the collision operator, which is modeled with the equation below. where we have the probability density function at the thermodynamic equilibrium. It depends on the lattice-Boltzmann methodology, but then this collision operator is adopted in power flow, which is the tool we use now. And then, so to understand the difference with Navier-Stokes equations, with Boltzmann equation, we describe the evolution on the microscopic scale. The lattice-Boltzmann is the discrete approach to solve the equation, while the Navier-Stokes equation describes the evolution of the macroscopic fields, such as the velocity, pressure, and temperature through the governing equation of fluid dynamics, which is the conservation of mass, momentum, and energy. We can link the Navier-Stokes to the lattice-Boltzmann with if the Knudsen number, which is the ratio between the microscopic scale and the reference length of the problem, is less than 1. So you can use the continuum assumption. And this is usually done by asymptotic expansion. So from the Boltzmann, from the Boltzmann equation, we can get to the Navier-Stokes equation under some constraints. Regarding low fidelity, variable fidelity methodologies, we have vortex particle method we adopt in our low fidelity framework. This method describes the particles as with a Lagrangian approach that track the evolution of the circulation of the particles, and basically it's discretized the Navier-Stokes, the momentum equation of the Navier-Stokes in its velocity vorticity form, so it becomes like a balance of angular momentum. We have on the left-hand side the evolution of the circulation of each particle, and on the right-hand side we have the convection, the contraction, and the expansion of the particles, the effects of multiple particles of the particle on each other, and the effects of the dissipation with the advection and strain pairs. So in general, we use an open source vortex particle method below. It's a reformulated vortex particle method because it adds some terms that enhance the continuity equation actually, and so the balance of the angular momentum, and also it adds the subfilter model, which is the last one on the right, which can model the dissipation of the vortex. In flow unsteady, each blade is then discretized into blade elements that incorporates 2D airfoil data, such as the lift and drag coefficients. And then with the Kutta-Joukowski theorem, we can reintroduce this circulation in the flow field based on the load distribution on the blades. Clearly, the high accuracy and the method is already been validated a lot in the literature with different test cases with multiple VTOL designs, but its high accuracy and low computational cost makes a good solver for the VTOL design and study different type of architectures. Then we couple with the aerodynamic solver with an acoustic solver we developed in-house based on the Parasat formulation. The Parasat formulation is a time domain approach. It's based on the Fox-Wiliam-Hawking analogy for a compact dipole monopole source. Basically, we evaluate the integrants at the retarded time, which is we have three main time grids. The emission time grid, where the signal is emitted from each blade element, the observer time grid. That is the time at which the receiver perceives the sound, and then the retarded time, which is reconstructed solving this implicit equation. So basically, fixing the observer time, you can reconstruct where was the blade at this, when the blade emitted this specific signal. Then, for considering also the kinematics of the solver, we solve each equation for each blade element, each blade for each time step, so we can have a description of the translational and rotational motion of the propeller. So we can have finally a pressure signal that is a function of the time and the position of the rotor and its attitude. So this is it's basically how it's coupled. We have this pre-processing block, and the processing with the aerodynamic and acoustic solver, and then we post-process the pressure data. Here, clearly, only the tonal noise is computed. We neglect the broadband. We neglect the quadrupole term because for our application, the Mach numbers are very low, so the quadrupole is not it can be negligible, but we don't have a broadband model for the low fidelity approach, not for the transient. We validated with respect to high fidelity and experimental data from the literature. Here you can see thrust, torque coefficients, and the efficiency of the propeller as a function of the advance ratio. This is the ratio between the free stream velocity and the rotational velocity of the propeller in RPS multiplied by the diameter of the propeller. And then we compare also with this data from the literature, the loading and the thickness noise with comparable results. Then we compared in a cross-flow configuration for the data also in the literature in the article below. And in cross-flow, we consider a condition in which the free stream velocity vector is inclined with respect to the rotational axis of the propeller. So we have a load and balance during the rotation of the propellers with some pressure level directivity that clearly changes its shape from dipole to something more less symmetric. We then validated with respect to experimental data. Here I will go a bit faster because it's we consider again the aerodynamic performance. Also in this case, we have good agreement with the experimental data, except for the torque, which is difficult to capture, especially for low Reynolds number propellers, where with low fidelity approach you can't capture the actual fluid dynamic effects that appears on the propeller. Then we measure some pressure level for different microphones in an array, circular array. So in this case, some pressure level directivity is in agreement with the experimental data for the first blade passing frequency. Then we consider some pressure level divergence to observe if the near field, far field terms are in agreement with respect to the experimental data. And yeah, also in this case, we've seen a good agreement. And then we compare it for a complete quadcopter, only the first BPS, considering the installed configuration both for the experiments and for the aerodynamic. Clearly, with the low fidelity approach, we don't simulate black bodies. we can only simulate interacts between lifting surfaces. And then we try to understand what happened during a transient angular velocity for the same propeller we used for the validation. Here we also performed some high-fidelity simulation with the lattice-Boltzmann approach. Here you can see the computational domain, which is made of variable resolution regions and the locally rotating reference frame, which rotates with the propeller with a sliding mesh approach. The minimum voxel size, which is the size of the cell, is 78 microns. We performed a mesh-independent study, and we choose the finest mesh. We compare the results for the initial condition. Here we perform a transient angular velocity from 5,000 RPM to 6,000 RPM. We compare the loading distribution along the radius and the force that produces the crust. We compared also the pressure data for two different observer location in the plane and out of plane. Clearly, out of plane, the broadband dominates the pressure field, which is not captured by the low-fidelity approach. We compare the first blade passing frequency between the two approaches. The second, we had a good agreement between the first and the second, while the third is underpredicted out of the plane of the propeller. As can be seen also from the spectrum. Here, the high fidelity, the red one is the total high fidelity spectra, considering also the broadband. The other two are performed with time synchronous phase averaging to wait.
Oh, it got to the end.
Okay. Clearly, during the transient, the velocity increases. Here it's just a video of the increase of velocity for with the rotating with the propeller. We can see the complex fluid dynamics on the regime because we can see a laminar separation bubble, which affects the noise, affects the aerodynamic performance, which is not captured in the low fidelity approach. And this laminar separation bubble moves, increasing the velocity. But considering the total thrust and the total torque, we have also a good agreement between the high fidelity approach and the low fidelity. And also for the pressure signals, here we consider the acoustic pressure as it calculated by Farasat. However, our main goal was to compare the shape of the pressure signal for different locations with respect to the high fidelity data. Here it's included, you see for observer close to the propeller axis, you see we have this mean, which is not being subtracted here because it's related to the variation of this mean, which is not acoustics. But we wanted to compare the shape and what drives the shape of the pressure signal. Here we consider the forces, so what happens to the forces in a global reference frame. So fixed with the inertial reference frame, fixed with the observer. We can see that the components of the forces with the components of the drag forces change and increases during the transient, and also the thrust. However, what's important, what comes in the equation is the radiation force, which is the force that the observer feels actually, which is projected in the radial direction with the observer. We see it in the plane, which mainly dominated by the Fy and Fz, which are the components of the torque of the drag, because the thrust is orthogonal to the radiation vector in that direction, so it doesn't account in the equations. While for observer closer to the propeller axis, we see that the thrust shapes becomes dominant. And also we can see here calculating the sun pressure level from the pressure fields I showed you before. We can see this we can see two overshoot of the sun pressure level, which are related to the beginning and end of the transient, but also this overshoot, which is related to the variation of the mean of the pressure signal. If we subtract it, we don't have the overshoot, but we still have the overshoot at the beginning and the end of the transient when the rotor starts to accelerate and then stops. Here it's just a video showing the rotor is rotating, it's increasing the SPL, and we see the increase in SPL at the beginning and the end of the transient for observer close to the propeller axis. And this is mainly due to the thrust variation. While for observer in the propeller plane, the torque variation is relatively small, so we can't appreciate large differences or overshoots. Considering a tilting, we studied firstly the tilting. Tilting is a change in attitude of the propeller, so it rotates along another axis, not only the axis of rotation, but it's also changing the attitude. We studied first a static tilting, which is just inclining the free stream vector with respect to the propeller, which is the same of inclining the propeller with respect to the free stream vector. We populated a map with aerodynamic performance of these conditions. We can see for fixed tilting angles, in particular for gamma equal to 0. Here I reported with alpha, but it's gamma. We can see that the thrust coefficient decreases, increasing the axial velocity, while it increasing the tilting angle. Here we can see also the root mean square. In particular, it decreases, increasing the free stream vector, free stream velocity, but in the hovering case we have an increase because it's a challenging also configuration because the rotor encounters its wake and the tip vortex doesn't travel fast in the wake. Here it's just a representation of the flow field for J equals 0.2 for an advance ratio 0.2 in axial inflow condition. And we can see that changing for the axial inflow, changing the axial velocity leads to a reduction in the induced velocity, and the tip vortex becomes weaker, as can be seen from the figure on the right and on the left below. Also, the tip vortex travels faster. This can be explained using blade element theory. Here, the total relative velocity is composed of the axial velocity and tangential velocity with respect to the airfoil. Clearly, the axial velocity and the tangential velocity depends also on the free stream vectors and on the induced vectors by the loads and by the loading conditions. Here, with the tilting, we have the free stream vector is inclined, and also the axial and tangential velocity affects the angle of attack, which finally affects the thrust and the torque. In particular, we can see that observing the radial distribution of the angle of attack for different axial velocities, we can observe that the induced velocity by the tip vortex that reduces the axial inflow becomes weaker, increasing the advance ratio, and the thrust also reduces along the blade, while the torque it's not really affected. And we have an axisymmetric distribution of the thrust and the torque. Considering the acoustics, we have changing the advance ratio for an observer placed in the plane of the propeller. We don't have much differences because the torque is not highly affected, while for observer close to the propeller axis, the thrust again dominates the radiation force. Increasing also the advance ratio change the SPL along the propeller axis, because for low advance ratios we have a fluctuating part in the thrust coefficient that is caused by the wake congestion of the propeller. For non-axial inflow configurations, we have that the rotor blade, rotor wake loses its symmetry. We have a load imbalance that highly affects the noise. And as can be seen here, these are phase average distribution of thrust, relative velocity, and angle of attack. The thrust is affected, depends on the relative velocity, the dynamic pressure, and the thrust coefficient, which is affected by the angle of attack. We can see that from the figure on the left, increasing J and increasing the advance ratio and increasing the tilting angle, we have this load imbalance. From an axisymmetric distribution, we go to a highly asymmetric distribution. Tracking interval along the blade for varying the azimuthal location, we can see for different inflow configurations that we have the peak of the thrust, which is mainly unaffected. We have J04 is in high advance ratio, so we have also this effect, which was observed also in this figure. We have this increase of angle of attack, which affects is affected by the reduction in axial velocity based on the blade element theory. So basically, the thrust follows the contribution of the relative velocity and the angle of attack. The sound pressure level distribution clearly differs from that in axial inflow. We have that increase in J, we have an increase in SPL along the propeller axis, and also fixing the J, we have a different shape also in varying the tilting angle. And here we have a comparison with the spectral with increase in J that increases the sound pressure level of the harmonics, while it's mainly in the rotor plane. This is in the rotor plane. It's mainly affected in the rotor plane. Okay, and then finally we perform the dynamic tilting. A tilting which the propeller changes the attitude in the axis of in the hub axis, so it doesn't have like a shift. It's just tilting in its along its hub. And we have that we have a load unbalance here also in this case during the transient. This is performed in hover. So we have this wake ingestion that highly influences the thrust coefficient of the blades. This is the tilting law, an error function, a fast transient from 0.1 to 0.2 seconds. This is the thrust and the torque coefficients during the transient. You can see that the increases during the transient, they decreases again, and then they still are bigger than what they were before the first steady conditions because of the wake. We see that also the blade with a single blade element, we have the shift. It's there oscillating in counterphase by the two blades because one encounters the wave while the others the clean flow. Increase in J, so with tilting in a forward flight, basically, we have that the thrust coefficient starts to oscillate higher than what was for J equal to 0, and also the torque coefficient. Here we have a representation of the tilting in hover. So basically, it changes the orientation of the lobes, and for the forward flight. And we have in this case it's more dramatic with a bigger increase in sound pressure level in the advancing side of the propeller. The flow is coming from here, this side. If we consider a plane, here it's considered a plane. So we can see the plane we see on the figure for epsilon equal to 0. You can see that approaching the propeller axis, we have these undershoot, which are governed by the loading noise, because the thickness noise is not doesn't have interesting shapes for an observer in the propeller plane, which always sees the propeller in its plane. The thickness noise is constant, while it changes if the observer is placed behind the propeller, while the propeller is tilting. If we focus on a single blade element for an observer behind the propeller along the propeller axis, we can see the global forces, how they changes, but we're more interested in the radiation force. And also to explain this undershoot, we saw the derivatives of we saw that the main actor is the derivative of the thrust along the radial direction, which has a like this undershape, which appears in the far field term of the Farasat formulation, which appears in the far field term of Farasat formulation, which is represented here. And then this is still going. We are studying the effect of single frequency harmonic gust on a propeller. It's doing in collaboration with other people from Delft and Mario from Turing. We performed high-fidelity simulation with a single frequency harmonic gust and with different wave numbers. Here is the test matrix. Here I report just one configuration, which is the case 1, the case 4, which is the gust with phase shift of 90 degrees. So it's following the blade. It's following the blade rotation with a frequency of 100 Hertz. We compare the results for the steady configurations. This is the representation of the flow field. And then we compare, for this case, we see that encountering the gust, it causes the blade to oscillate in counterphase. One increases the mean CT, one decreases the mean CT because encounter different inflow conditions, but they're synchronized with the gust. So one blade always encounter an increase in velocity, and one blade always one decrease in velocity. We compare with the high fidelity result. We see that we have additional harmonics that are depends on the frequency of the gust, but the harmonics of the propeller are not affected by the gust. You can see also on the right the difference between the clean case and the gust. Then we will study more different type of gas and so on. So to conclude, noise prediction under unsteady condition remains challenging, in particular in understanding what physical mechanism alters the noise levels and its directivity. Low fidelity approaches seem capable of capturing these phenomena, offering a lower computational cost in minutes or hours with respect to days and weeks of Lattice-Boltzmann simulation and months of Navier-Stokes simulations. Major drawback, of course, of the low fidelity approach is that the broadband contribution is not included, and it is difficult to model in a transient condition. But also with these low fidelity approaches, it's easier and less expensive to perform parametric studies and acoustic optimization of maneuver, taking into account physical noise metrics and sound quality metrics. Also because here it's not clear what's the reference configuration of the VTOL. It's not clear what's the flight path. So in order to perform a parametric study, it's, I think, better to do it with low fidelity approaches. With that, I conclude, and thank you for your attention.
Thank you, Marco. Time for questions in the room or online.
With this low fidelity method, do you produce plausible kind of oralizations to kind of listen to?
Yeah.
Or do they sound realistic, or do they just sound like just tones or?
Mainly tones. If you don't have the broadband, I never try to do it, but yeah, it's without the broadband noise. It's mainly only tones and only.
But you can produce them at kind of like a realistic sample rate and actually
Yeah.
reduce polarization if you.
Yeah, with the signal. Yeah, because I have from the low fidelity tool, I have like a pressure signal in time, so I can manipulate the way I want.
And is it? I'm guessing it's non-trivial to extend this to say if you had two propellers.
Yeah, you can do it.
Do that even if they're relatively close, or do you have to assume that they don't interact with one another?
No, I mean you can't model the acoustic interaction in the near field. You can model the aerodynamic interaction, so study what are the effects of the interaction on the noise and as an observer, but without considering near field effects of the acoustic.
Okay.
Yeah, Marta, please.
Yeah, I have a couple of questions about the CFD solvers. So first, like the vortex method that you described, I've heard about it before, but I don't know much about it. So can it do turbulence?
I mean, if you read the thesis, yes.
Okay.
I don't know. I never performed studies with turbulence. You can't produce the turbulence. You can't. I mean with this approach. But when the vortex with this particle, you can study the vortex evolution and the fragmentation. Then finally it goes like turbulence. So in theory, if you have a lot of particles, you can also simulate the turbulence.
Oh, okay. Yes, I understand. Okay. And the second question is about power flow. So power flow is a commercial software.
Yes.
And so when it comes to run your LBN simulations, where did you run it? Did you need supercomputers?
Yes.
And which supercomputers did you use? Because I know that at least here, some supercomputers have restrictions on using commercial softwares in them and things like that.
We use the cluster in Turin.
Oh, okay.
Yeah.
Okay.
So we have a cluster.
Okay.
Yeah, because it's very expensive.
Just out of curiosity, how much did you need to run? Like how many, is it the GPU solver?
You mean to prepare the case or to how much is a simulation?
Yeah, I'm just asking how much is one of the LBN simulations cost.
For the steady simulation, 3 to 4 days. For the transient, because it was a bit coarser, 8 days.
And how much resources?
With not much, 5 nodes times like 100 CPU per node, so 500 CPU.
Okay. All right, okay, thank you. Sorry for the lot.
No, that's all right. Thank you, Marta. Mike Latino, do you want to use your microphone or do you want me to ask you a question?
Oh, thanks, Antonio. Well, actually, I should make way for Deepak, who had his hand up first. I just wrote mine in the chat.
Sorry, I don't. Apologies. Yeah, Deepak, go ahead. Sorry.
No, like I hope I'm audible. Hello?
Yeah,
we can hear you.
Yeah. So my question was, you tried to use the methodology what you did for quadricopters, am I right?
Yeah.
Yeah. So, but how did you use the Faraset A for the quadricopter? Did you assume that the rotors act independently and they do not interact with each other?
Yeah, they don't interact in an acoustic way with each other, but with I took like the aerodynamic loads of each rotor. And then I performed a simulation for each rotor at an observer with the same time grid of the observer. And then I reconstructed the emission times of each rotor. So yeah.
Yeah. So you mean to say you did independently for each rotor?
Yeah.
Okay. Yeah. Thanks.
For the acoustics.
Yeah.
I think, sorry, Mike, I think that's related to a question before from Jost.
Yeah.
Is that a fair assumption? Because there should be some, I understand.
If you're in the far field, it's a good assumption. There's a lot of people actually that use Farasat with installed configurations. and seems to produce reliable results.
Yeah.
So,
Okay.
I mean, yeah, there could be some install effects like rotor interacting with the stator behind, and maybe have potential interaction or the wake interactions. Yeah, but somehow, like if you're trying to estimate unsteady or overall aerodynamic effects on the blade, then it captures some part of it, but not the whole, because the noise may not be just coming from the rotor, but there could be some stator elements like you have the rod or
yeah,
the
of course.
airframes. Yeah, that's
Yeah,
right. It's
black
so,
bodies are not modeled.
yeah.
This approach, just the interaction between the rotors from another aerodynamic point of view.
Yeah, and then acoustically you're assuming that they're acting incoherent, and
Yeah.
you just add the pressure. Yeah, okay, that's
Yeah.
Okay, thank you, Deepak. Mike?
Yeah, thanks, Marco. I've just had a sort of high-level outlook question, which was about what the potential might be for developing hybrid approaches that combine low and high fidelity, and whether there's any computational benefit there. I'm kind of thinking along the lines of some of the stuff that's been done in room acoustics, where they've kind of tackled some of these problems using hybrid approaches.
Yeah, I mean, there are many methodologies also using run simulation with Parasat to better capture loading distribution with but the main goal here was to use a low fidelity approach, take as less resources as we can to understand if it's a reliable approach. Of course, also this vortex particle method is variable fidelity, depending on the discretization of the blades, how you reconstruct the blades, how many particles you shed during each time step, how you treat the solver, if you add the viscous or effects, or if you use just inviscid solver, depends on the simulation. I don't know.
Yeah, so would it be good to use the high fidelity to get the broadband side, and then just use low fidelity to combine it?
Of
the
course.
tonal from the low fidelity. Yeah. Thank you.
Thank you.
Thank you. Any other questions in the room? Marta?
Just one question. I don't know much about sound, so maybe this is easy to answer. But so could you get this broadband using Rand's methods or not?
With runs, no, because I mean runs are steady simulation basically.
Yeah, so you need time variability.
Yes.
Yeah, okay.
So,
I mean, yes.
sorry, Deepak.
No, I mean you can get broadband, but it's no, you have a mean distribution of
Okay.
Deepak, sorry.
There are some sort of semi-empirical models. If you get some sort of information from the runs, like how your boundary layer thickness has grown over your like blade profile, and so if you know some sort of boundary layer features, then you could feedback these things into the M8 models, and then you can get some sort of broadband noise.
Yeah, but not if you are studying like an unsteady condition with the runs, you can't get you don't get the actual broadband of the maneuver, because the runs is just averaging.
Yeah.
So going back to your case with the cast, what is going on here? So, for example, there you have you have some extra discrete tones. What's going on there? Can you explain?
Yeah, because the gas is coming from the cross flow direction. It encounters one blade with the increasing velocity, while the other with the decrease. So you have this load and balance, which is the same frequency of the gas. And so we see that the loads start to oscillate, and then we have an increase also in the mean thrust coefficient because the blade is more loaded because of the increase in the velocity, while the other one is.
So
the
these
mean thrust is the same.
these studies is there any change in the thrust? So this thrust.
The thrust is basically if you consider the global thrust, it doesn't change. In fact, you don't see effects on the first BPF.
And what you have here is high fidelity, low fidelity, and you look at tone and noise. You're looking at. Do you have experimental data for this as well, just to see what's going on with the broadband? Or...
No, here the high fidelity.
Oh, the
there's also the broadband.
Oh,
here
yeah.
I cut it at 3000 hertz. But yeah, the high fidelity is the.
So there is no. So
no filters, nothing.
So what's going on? Looking at the high fidelity,
Yeah.
what's going on when you have the gusts? Is there an increase in
I mean, focused on for now on the broadband part. Just I was curious to see if the tones are the same with the two approaches. But I mean, it's increased. I think I don't know. I will see because yeah, I cut it at 3000 hertz, but at I saw the spectra along the propeller axis, and the broadband seems to have the same shape of the broadband from a steady simulation. I mean, from a steady condition.
So is your assumption then that mainly tone and noise would be?
Yeah, because I think so, because
it's interesting from the perception point of view. Any other comments here? Or
Just one question about it. So you mean that the gust frequency is driven by the angular velocity of the propeller, or you can control?
No, the frequency is fixed of the gust, but we choose 100 hertz to see. I mean, because the rotation the BPF is 200.
Okay,
so
the gust frequency.
Yeah, I choose it.
Yeah.
So when you say gust, you mean that this is the change in
the velocity, free stream velocity.
But I guess in reality, that's kind of stochastic, it's random.
Yeah.
So you wouldn't actually expect to see these secondary tones. You'd probably see an increase in broadband level instead.
Yeah. Also, yeah, but I mean, it's not. It depends on the stochastic. It's not very only stochastic. Like a Karman wake, it's not stochastic.
Okay.
It has a frequency, a Strual number, which a clear frequency of the shedding of the vortices. So
I think Marta can comment on that.
But I was just thinking, if you are flying close to buildings and the buildings accelerate the wind, then you would have like gusts that are quite maintained as long as the wind continues on that direction and the QMB stays dead.
Yeah, this is just a reference gust.
Yeah.
It's not, of course, because it includes the turbulence.
Yeah, so far. I think there's another PhD student interested in looking at this in more detail, right, Mario? Yeah. So we will talk to you guys. Yeah. Any other thing, or should we?
Antonio,
Deepak.
Can I ask? Yeah, I think what happens is like you assume that the gust has a some fixed harmonic frequency, right?
Yeah.
So it's like having a rotor upstream of your like propeller. Okay, so it is ideally it is a classical problem of rotor-rotor interaction, and those in between frequencies you see, those are like a sort of interaction tones sort of, but they are like of fixed gust. So that's why you get those in between things. And regarding this broadband noise in your high frequency, you can see there's a slight increase at the broadband noise at the high frequency. And this is a typical case of leading edge broadband interaction noise source, and that hits starts hitting somewhere like around 2000 or 3000 hertz maybe for this sort of propellers. And yes, and yeah, this is a sort of the range where you get the leading edge broadband interaction noise.
Okay, thank you, Deepak.
Thank you.
Thanks.
I think we can conclude now the seminar. Thank you, Mario.
Thank you.
Really interesting.
Thank you.
Thank you. Thank you, people online.
You warming up, getting vocal at the school meeting.
No problem.
You teach them.